This tutorial describes how to modify a data collect setup so it can be used in combination with the machine to perform inspection, rather than manually controlled by an operator. The following steps will be required. Create a manual setup, which is done in other training videos. 2. Perform basic changes required for automation. 3. Define automation requirements. 4. Define machine handshaking. Then 5. Add handshaking signals to setup. 6. Add automation script source. 7. Add calls to automation scripts. Then 8. Test. This tutorial, again, will skip item 1, refer to the many other tutorials to learn about creating manual data collect setups. Step 2. Prepare for automated inspection by turning off the sequence selection screen. Click the Setup button and then the Setup Editor option. First, disable the part summary and then click Computer Options. Click Preferences. Then remove Show on New Part Selection. Return to Gauging. Step 3. Now define the automation requirements. Our sample setup is very simple and consists of a single inspection step performing one measurement. However, the approach that will be used can also be used for sequences with multiple inspection steps. Inspection requirements for this sequence are: 1. Machine places part in fixture. 2. Machine requests data collect to inspect the part. 3. Data collect acknowledges the inspection request. 4. Data collect performs the inspection. 5. Data collect provides the inspection status. 6. The machine removes the part from the fixture. And then 7. Repeat from step 1. Step 4. Define the handshaking. Implementing the automated sequence requires that data collect communicate with the machine. This is done with discrete signals between data collect and the machine. Using discrete signals is typical of how machines have operated for decades and provides an easy test and troubleshoot interface. Discrete signals are always one way and are controlled by either the machine or data collect. Never configure a discrete signal such that both the machine and data collect will change its state. The first signal required is for item 2. This signal is from the machine to data collect and it indicates that the part is ready for inspection. We'll call this signal take data. It is an output from the machine that will request data collect to inspect the part. This will be a machine output and a data collect input. The second signal required is for item 3. This is an acknowledgement signal that informs the machine that data collect has received the take data request. We'll call this signal take data ACK. It is an output from data collect that informs the machine that the request was received. This is referred to as a handshake. It is good practice to implement machine communications with handshaking. This will be a machine input and data collect output. The third and fourth signals required are for item 5 and are used to send inspection status to the machine. These will be part accept and part reject signals. One of the two signals will be turned on after part inspection is completed to inform the machine of the inspection results. These are machine inputs and data collect outputs. The last recommended signal is also used as part of item 5 and signals the machine that part inspection is complete. This is the DC complete signal. It is turned on after all part inspection is completed. This is a machine input and data collect output. Step 5, add handshaking signals to setup. It's now time to add the defined handshaking signals to the setup. Data collect booleans are used to interface with discrete signals from the hardware interface modules. Click the Hardware button and then the Definitions option. We have a total of 5 signals that will be used. Enter the name of each signal in the name field for the first 5 booleans. Now that the names have been entered, the Boolean source property must be configured to connect to the HIM. The most common HIM used to communicate with machines is the OPC HIM. Configuration of the HIM will not be discussed here. Documentation and tutorials describing HIM configuration are available and should be reviewed. For our purposes, we can assume that the HIM has been configured and that the first HIM Booleans have been configured to correlate with the 5 required signals. Map the source of the first 5 data collect booleans to the first 5 OPC HIM booleans. We can now return to the gauging screen and test our discrete interface. Click Data Collect and then the Gauging option. Click Hardware and then the System Values option. Now we can test each of the discrete signals. From the machine, turn on the Take Data signal. If the OPC HIM and Data Collect Boolean source mapping is correct, you will see the Take Data value change from false to true. Turning the value off at the machine should return Take Data to false. Now we can test each of the discrete signals. Next, click the Value column for each of the data collect outputs. The value for the output should toggle each time the cell is clicked. Each time you toggle a value, verify that the corresponding value changed at the machine. If any of the signals were not observed properly at either the machine or data collect, then an issue exists with the configuration of the machine, HIM, or data collect and must be resolved. Step 6. Create automation scripts. The discrete signals required for communication with the machine have been created, but they are not yet being used. This step creates script functions that will be called to communicate with the machine using the defined signals. Click the Setup button and then the Setup Editor button. Click a sequence object that allows script calls to be added. A good choice is an inspection node in the sequence tree. Click the Source option. Click the Add Edit Units button. All scripting is created using this option. The Inline Source button is used to add calls to script functions and will be used later. The first step will be to create a unit to hold the functions that will be created. Never modify the main source unit. This unit is automatically generated by Data Collect. Any changes made to the main unit in the source editor will be lost when DataCollect regenerates the inspection source. Also, the visual elements to the right of the script editor should never be used as part of the inspection sequence scripts. The inspection sequence script runs as a thread and therefore cannot reliably access the user interface. Using visual elements will have unpredictable results and may cause DataCollect to present random errors. Click the File menu option and then New Unit. Click OK to set script source type to Pascal. The source in this tutorial is Pascal. Scripts can also be programmed in BASIC by selecting BASIC in the drop list and then clicking OK. Once the new source unit has been created, the required functions can be entered. At the top of the unit, constants have been created to make accessing the defined booleans easier. Using constants also makes the script easier to support in the future. For instance, if for some reason the boolean used to set the accept output must change, the script change can be made in one place. The constants are used wherever a signal is accessed. The highlighted area shows the part accept and reject signals being turned off. The global takeDataReceived variable keeps track of whether the script has observed a takeData request from the machine. The initSeq procedure is used to initialize output signals at the beginning of part inspection. One call to this function will be used at the start of each part inspection. The checkTakeData procedure is used to check for the takeData signal from the machine and provide the takeData handshake. If the takeData signal has been received, the procedure moves DataCollect to the next inspection step after handshake is completed. A call to this function will be placed in each step of the inspection sequence. The setPartStatus procedure is used to set part status outputs after inspection is completed. The DataCollect internal part accept and part reject library calls return the current status of the part. This function will be called one time from the inspection sequence after part inspection has been completed. The setComplete procedure is used to set the inspection complete output after inspection is completed. This function will be called one time from the inspection sequence after part inspection has been completed. Next, let's save our work. Click the File menu and then the Save option. Enter the appropriate name for the source unit and click the OK button. Calls to the functions in the new unit will be made from the main source unit. For this to happen, the main unit must have access to the new unit. A simple change is required to the main source unit to provide the required access. Click the Step Main tab to display the main unit's source. Add the new unit to the Uses clause of the Step Main unit. This is the only area of Step Main that should ever be modified. Everything below this line is automatically generated by DataCollect. Any changes made after the Uses clause will be lost when the DataCollect regenerates the source. Close the script editor. When prompted to save changes, click Yes. Step 7. Add script calls. This step modifies the inspection sequence to call the script functions that were created. A second inspection step will also be created to display the final inspection results and complete the machine handshake interface. It is common to have an extra sequence step at the end of a sequence on automated inspections. The first script call is adding the initialization call. This will be added to the part inspection sequence before inspection section. Activate part sequence display and then select the before inspection node. Click the source option and then select inline source. Type the name of the initialization function and then click OK. The initialization function we created is an initseq. All Pascal source lines end in a semicolon. Click the Step 1 inspection node to add a call to the check-take-data function. Click the source option and then select inline source. Type the name of the check-take-data function and then click OK. The check-take-data function we created is check-take-data. All Pascal source lines end in a semicolon. Click the gauge sequence node so that a second inspection step can be added. The second step will be used to display part inspection results and complete the machine handshake. Click the step option to add the step. Activate showing of step states. This will display the begin, inspection, end step states and allow calling script functions at the beginning of step 2. Click Before Inspection and then the source option, followed by inline source. Enter Set Part Status to call the Set Part Status script function we created earlier and then click the OK button. All Pascal source lines end in a semicolon. Click Before Inspection and then the source option followed by inline source so a call to setComplete can be added. Enter setComplete to call the setComplete script function we created and then click the OK button. All Pascal source lines end in a semicolon. Click Inspection and then the source option followed by inline source so a call to check set data can be added. Click Inspection and then the Page Editor option so a page for step 2 can be created. Copy the page from step 1 to step 2. Then modify the screen heading. Then exit the page editor. Step 8, Test. Return to Gauging to test the setup. Click Hardware and then System Values to display live system values. Click the Booleans tab so that discrete handshaking can be observed. Run a cycle at the machine. The take data signal should be activated by the machine and responded to by data collect with the take data act signal. Data collect will move to step 2 after the machine clears take data in response to observing take data act. Observe the part status and inspection complete signals have been set up in step 2. The take data/take data act handshake must be performed again to exit step 2 and return to step 1 and wait for the next part. So here's an example of Orbit Gauge Software 4.0 actually being connected to a robot. Here the robot is picking up a part and then placing it within the gauge based on the commands from the software. Also, it is telling it whether it is a failed part or a passed part. And then here's a close-up of the gauging process itself. And again, all data is recorded and tracked using the software package, which includes SBC features. All training videos for Orbit GaugeSoft are also loaded onto the Solartron YouTube channel. Just scroll down, and if you'll see Orbit GaugeSoft 4.0 training, every single component will be loaded right here.